Hello and welcome back to chemistry. So today we're going to talk about the Arrhenius model of acids. Now, there's a lot of different models, a lot of different ways to look at these substances of acids. And we've started by looking at the classic models and the classic definition of acids, the classic properties of acids, and the resulting von Liebig model of acids that lasted for about 50 years. All those models were based on the properties of these substances. They weren't based on the idea of atoms and molecules. For that, the first modern theory, or when we started looking at acids and bases, based on the model of atoms and molecules, was given to us by Svante Arrhenius. Now, Svante Arrhenius was a prodigy, and he came up with a number of very important discoveries. Perhaps the most important discovery, what it was argued to be the most important discovery for the next 100 years of chemistry, was the theory of electrolytes. There are certain materials that exist as a combination of cations and anions, and when you dissolve them in water, they dissociate. Things like sodium chloride or potassium nitrate. When you dissolve it in water, it dissociates and it gives you those ions. Svante was the person who explained to us that we weren't creating ions by running electricity through water. We were instead discovering these ions that came out when we just dissolved sodium chloride in water. Now, when you're most famous for building a hammer, pretty much everything in the world looks like a nail. And many of the things that Svante Arrhenius later discovered and helped us understand, many of those things were based on that theory of electrolytes, including his theory of acids. So what he suggested to us is maybe an acid is a material that is composed of, this is an electrolyte. It's composed of an A half and a B half, where the A half is a cation and the B half is an anion. It's just that in the case of an acid, the A half is specifically the hydrogen cation, hydrogen ion. And when you dissolve this in solution, well, that kicks off H+. H+ floating around in solution then gives us all the properties that we'd come to know about acids. He also described the bases in a similar way. He said they were a different class of electrolyte, an A half and a B half type of molecule. But the B half, in the case of bases, was composed of hydroxide ion. Again, when you dissolve it in water, it increases the hydroxide ion concentration, and this gives us the properties of our basic solution. Now, when we talk about electrolytes, we classify them as strong electrolytes or weak electrolytes or negligible electrolytes based on their tendency to dissociate. It's kind of counterintuitive. Strong electrolyte dissolves completely in solution, falls apart. Strong falls apart. Why? Because it gives us a strong concentration of ions when it falls apart. So a strong electrolyte is one that falls apart easily. And if we use that model to understand acids, then we can start to sort acids in the same way. The acids that fall apart completely in solution are strong acids. Now, remember, when we say they're falling apart, we're talking about the A half or the hydrogen ion falling into solution. Now, hydrogen ions are arguably the strongest source of positive charge the human species knows about. I mean, a hydrogen atom is just a proton and electron, and if you have a hydrogen ion, well, you take off that electron and you're just left with a proton. So one thing to be careful about is hydrogen cations and acidic solutions that are built from them can be very dangerous. So be very cautious when you're working with acids and bases in the laboratory. All right, but back to the idea of the strength of these solutions. If we want to try and understand the strength of acids, again, we will use the analogy of electrolytes. Strong acids are those that dissociate completely. We say a strong electrolyte is something that dissociates 100% to 3 sig figs. And so we'll say a strong acid also is something that dissociates to 3 sig figs. In contrast, a weak acid is one that dissociates, well, somewhat, but lesser. Basically anywhere between 100% and 0. And so when we're looking at these materials, if you take a material and you put it in solution, you're basically putting as much H plus as you have of acid. We're not counting polyprotic acids just yet. But a strong acid dissociates 100%. There's a lot of strong acids, but there's 7 very important strong acids. These are the classic strong acids. These are the materials that exist in pretty much every chemistry laboratory. You can use them interchangeably when you just want to put protons in there, but they each have some unique features. Acids like sulfuric acid and nitric acid have some unique twist to them. They're 2 of the 7 strong acids. 3 of the binary acids are considered strong acids. Hydrochloric, hydrobromic, and hydroiodic acid are strong acids. And then the last 2 are one of the strongest strong acids, perchloric acid, and one of the weakest strong acids, chloric acid. Chloric acid is actually right on the dividing line. Yeah, it dissociates 100% to 3 sig figs, barely. You can almost see the edges of it. Chloric acid is sometimes not considered one of the strong acids if you only look for 6. But most books will say 7 strong acids, and they will include chloric acid. Now, all of these are strong as simple. All of these, you put them in solution, 100% they become ions. No problem. There are other acids that when you put them in solution, they dissolve a little bit less. Now, remember when we talked about weak electrolytes, strong and weak electrolytes. Strong is simple, 100%, but weak can be 50% or 75% or 5%. When we introduced weak electrolytes to you, we made you responsible for only 2 classic weak electrolytes, hydrofluoric acid and acetic acid, both of which are also weak acids. Both of these dissociate about 5% in solution. So what does that mean? That means if I drop them into solution, well, 95% of the material is still an associated ion pair. And the other 5% on average is dissociated as, for example, fluoride ion and H plus ion or hydrogen ion. Okay, so this is a qualitative breaking down of acids into strong and weak. And right now, you're responsible for 7 strong and 2 weak. However, as we proceed, we're going to introduce many more weak acids. The weak acids, weak acid is kind of a misnomer. Weak acids are actually the most interesting of them. Strong is simple, just dissociates. But weak, you can play some games with. You can do some interesting stuff. Personally, I think it would be better if we had called them subtle acids than weak. But that's just me. And the industry calls them weak acids. Again, you're responsible for 2 right now, but more are coming. Now, if we want to get quantitative on this dissociation, well, how weak is weak? And strong is 100%. That's simple enough. But how weak is weak? Well, we can look at the degree to which they dissociate. And yeah, we can use things like acetic acid dissociates 5%, another acid might dissociate 50% or 95%. And we can use that to compare the strength of different acids. But this is an equilibrium expression. We did a lot to explore KEQ. Might as well put it to some use here. We are going to use KEQ to measure the strength of an acid, a particular pure substance. To what degree does it dissociate? And you can look at the mass balance and therefore the equilibrium constant to see to what degree these materials dissociate. Now, when we're using KEQ to evaluate an acid, we're going to change that subscript from the generic EQ to the specific capital A. K sub A is the acid dissociation constant, and that's your measure of the strength of an acid. Someone asks you, is this a strong acid or is this a weak acid? What you want to look at is the Ka value. So, for example, for all the strong acids I mentioned, the Ka is 1 or greater. It's basically 100% dissociation to 3 sig figs. But the more interesting ones are these weak acids. and they will have a dissociation between 0.1 and 10 to the minus 14. And that's going to result in a dissociation that's, I don't know, somewhere between 100 and 0. Maybe it's 95%, maybe it's 50%, maybe it's 28%, maybe it's 5% or 2%. But all of those are considered weak acids. There is a third category, negligible acids. When a substance has a KQ of less than 10 to the minus 14, technically equal to or less than 10 to the minus 14, and it therefore dissociates about 0% to about 3 sig figs, then what we're talking about at that point is a negligible acid. We say non-electrolyte when we're talking about this classification for electrolytes, but we say negligible acid when we're talking about acids. What do we mean by it being an acid but negligible? We mean you can get dissociation out of this. You get some when you put it in water, but if you change the state, the circumstances that are in, that material is protic. You can get the proton off. It just doesn't fall right off. You got to get out and push a little bit. But negligible acids are still acids. It's important to realize that. Okay. The other thing we should probably talk about is the Arrhenius model also defines bases. Now, the nice thing about Arrhenius bases is they are much simpler than Arrhenius acids. Remember, Svante Arrhenius used that electrolyte model. If it's a base under Svante Arrhenius, then it's an AB material where the B half is hydroxide. So sodium hydroxide, lithium hydroxide, magnesium hydroxide, and calcium hydroxide are all Arrhenius bases. And you might say, well, okay, so which one's the strong one, which one's the weak one? Here's the trick. They're all strong. All Arrhenius bases are strong bases. And you might say, okay, Nick, I know sodium hydroxide is a strong base, and so is lithium hydroxide. But magnesium, calcium hydroxide barely dissolves in water. How can it be a strong base? It's because the definition is not about solubility. It's not about how much of it can get into the water. It's about when it does get into water, how much of it is an ion pair versus how much of it is dissociated. And for all these materials, the dissociation is basically 100%. So this makes Arrhenius bases maybe a little more complicated in one way, but simpler in others. It's not about the solubility. It's about, once you get it into solution, the dissociation. And all salts that are hydroxide salts, if you can get them into solution, are strong Arrhenius bases. All right, that's all we got for now. Next time we will take a look at different classes of acids, binary acids, polyatomic and organic acids, and we'll go through that. But I'll let you go for now. Hope you have a great day. Talk to you soon.